For decades, our digital world has been powered by a single, relentless engine of shrinking components. But scientists at the Vienna University of Technology have identified an atomic-scale gap that could prevent these devices from getting any smaller. We have structured our economy around Moore's law, the assumption that as we shrink silicon transistors, our computers will reliably become faster, cheaper, and more powerful. Decades ago, manufacturing limits were dictated by things we could easily see and touch. Engineers had to figure out how to physically assemble bulky, macro-scale electronics on open factory floors. Today, we engineer at a scale bordering on magic. We etch billions of individual transistors onto a single silicon wafer, packing microscopic grids so tightly they operate near the absolute limits of physical matter. This shrinking process is now colliding with a hard barrier. We haven't run out of capital or engineering talent, but we are reaching limits imposed by the laws of physics. We've built a global roadmap on the assumption of infinite miniaturization. Now the math suggests that trajectory cannot be maintained through traditional scaling. To keep pace with hardware demands, the semiconductor industry turned to 2D materials like graphene and molybdenum disulfide as a potential successor to silicon. These materials possess a unique structural trait. They can be engineered to be as thin as one single atom, making them candidates for building the smallest possible electronics. Convinced this was the path forward, tech companies and research institutions have poured billions of dollars into isolating and perfecting these ultra-thin layers. But when these pristine materials are integrated into functional chip prototypes, their performance often fails to meet expectations. By focusing strictly on creating flawless sheets of isolated material, engineers overlooked the complications that arise when those sheets are joined to the rest of a working device. The issue isn't the 2D material itself, but the fact that a transistor cannot function in isolation. It requires a partner to control the flow of electricity. A future transistor works like a microscopic switch. To function, it needs an ultra-thin 2D active conductor layer paired with an insulating oxide layer to separate it from the control gate. When manufacturers stack these two incredibly thin materials together, they are held in place by van der Waals forces, a relatively weak magnetic attraction between the atoms. Because this attraction is so weak, the active layer and the insulator never physically touch. A permanent empty space forms between them. The components themselves are well constructed, but the physical boundary connecting them creates a mechanical disconnect. This separation is incredibly small. When researchers measured the void, they found it spanned roughly 0.14 nanometers across. To put that measurement into perspective, the gap is thinner than the diameter of a single atom of sulfur. If you were to compare it to a SARS-CoV-2 virus particle, the virus is about 700 times larger than this microscopic canyon. But at the atomic level, distance behaves differently. This tiny void ruins the capacitive coupling between the semiconductor and the insulator. The electrical signal essentially hits a cliff, struggling to jump the gap and weakening the entire device's efficiency. This physical reality means that an empty space smaller than an atom can act as a wall, preventing us from making computer chips any smaller. Researchers at the Vienna University of Technology are proposing a change to chip architecture to bypass this physical limitation. Their solution involves creating a class of paired components, which they call zipper materials. Instead of relying on loose van der Waals forces to hold two flat surfaces together, zipper materials are engineered with atomic structures that interlock physically. By designing the materials to mesh structurally, the loose connection is replaced by a tight bond, entirely eliminating that 0.14 nanometer gap. With the two layers tightly bound, the electrical signal transfers seamlessly between them, restoring efficiency and allowing the hardware to scale down further. For these devices to work, the active semiconductor and its insulating layer must be engineered as a single unified system from the start. If manufacturing facilities can scale this production method, the atomic barrier is removed, and Moore's law survives into the next generation. We have reached the limits of finding one isolated substance and expecting it to carry the weight of modern computing. The next leap in computational power relies on mastering the complex architecture of the spaces between the atoms. Engineering materials at this atomic scale requires mapping thousands of possible structural combinations, a task suited for machine learning.